Hi everyone, Mr. Graham here. Just going to kind of show you a real-world example of the things that I talked about in the last video. So I have our good old motion detector here, our ramp. I have it at an angle now though. Remember last time we saw this equipment, we were talking about the constant velocity motion of this little buggy. But now we're going to talk about the motion of this guy as he accelerates up and down the ramp. Okay. And keep in mind that in physics, really any change in velocity is called an acceleration, even when it's slowing down. So we would say on the first half of the motion, that's accelerating. Yes, sometimes people say decelerating, but you can think of any change in velocity as an acceleration. You don't need to say deceleration. You just say that's accelerating, it's still accelerating, still accelerating, still accelerating. It's all acceleration, okay? So I'm going to show you with our motion detector, remember that uses sonar, I'm going to make a position versus time graph for the cart as it uniformly accelerates. Remember, this is motion under what's called UAM, uniformly accelerated motion. And sure enough, we get, now it looks a little different than it did on the computer simulation that we did. This is now, it's oriented differently. We have an inverted parabola now. Now think about it though. The motion up the ramp was to your left, which means if our coordinate system said that to your right, down the ramp was the positive direction, then it would have a negative velocity on the way up the ramp. Negative velocity here, we have a negative slope. And because it was slowing down, the slope was getting shallower and shallower and shallower until eventually it came to a stop where the slope was 0. And that was at the top of the motion. Then it reversed direction and sped up in the opposite direction. Hopefully that kind of makes some sense. Now, I also said in the last video that your choice of coordinate system doesn't actually matter. When it comes to physics, you can make your measurements from any coordinate system you want, and as long as you're consistent, you'll be describing the same motion to a reasonable degree of accuracy, and it's fine. So I'm going to go ahead and actually reverse the direction here. And so now up the ramp will be the negative direction. Will be the positive direction. I forgot. We'll see. Yes, up the ramp was the positive direction. Sorry about that, little brain fart there. So yes, I start in that particular coordinate system, I start with a positive velocity, and it slows down, comes to a stop, and then speeds up in the negative direction. So it's the same motion, just described graphically in a slightly different way, just because we have a different coordinate system. Typically, we say to the right is positive, whether it's slanted to go up or down a ramp, but it's usually to the right is positive, to the left is negative. So yeah, let's talk about the same stuff though with the velocity time graphs. I'm going to go back to the original direction, and then I'm going to bring up my velocity versus time graphs. Now again, uniformly accelerated motion, we should expect this to be linear. This graph should be linear. So let's see what we get here. Okay, it is linear. It is a pretty shallow though, so let's go ahead and auto scale it. And sure enough, it's pretty much linear for most of the motion. Again, the measurements here aren't perfect. There is a little bit of friction, a little bit of air resistance in the real world, so it's not going to be perfectly linear. But we do have a pretty linear graph here. This is when I was pushing it. This is when I stopped it. This is when it was just chilling. But this is when it was moving on its own under uniformly accelerated motion. So I started moving up the ramp in the negative direction. So I start with a high negative velocity, and it slows down, slows down, slows down, slows down, stops, and then starts speeding up, speeding up, speeding up, but then in the positive direction. Okay. And then if I just do it again and reverse the direction, then we'll see exactly what we saw whenever we did the simulated motion graphs. And sure enough, that's what we see. See a nice linear graph. We start with a high positive velocity, and then a little bit over 0.5, I'd say probably about 0.7 meters per second. And then it starts slowing down, slowing down, slowing down, comes to a stop, and then starts picking up speed in the negative direction. Notice positive quadrant. For quadrant 1, all values are positive. Quadrant 4, the vertical axis values are negative. And so these are negative velocities, these are positive velocities. Okay. Now I want to finish this video by talking about free fall. And I probably will have to... Where'd my position versus time graph go? Give me 1 second. Oh. Sorry guys, bear with me. Again, zero editing skills, so you're gonna have to watch all my mess ups. So now I'm gonna plot the motion of an object in free fall. And I'll probably have to do this a few times because it's really hard to throw the ball up above and keep it directly over that the screen there on the motion detector. But I'm gonna go ahead and plot the position versus time and the velocity versus time graphs both together. Yeah. Okay, so let me give this a shot. I think I actually got it. So let's blow this up on this interval here. And auto scale it. Oop. Zoom in there. Zoom in here. And this is pretty terrible. There we go. So notice on the velocity versus time graph, we have linear and it's sloping down to the right. Position versus time graph, it's hard to see, but that is a parabola. That is the quadratic that we're expecting to see. There it is a little more. Yeah, let's try this again. That wasn't the best. Let's try this one more time. That's much better. That's much better. All right, let's auto scale that. There we go. And I'll zoom in. Oops. I'll zoom in so we just see this part here. So again, this is when I'm throwing it. So I'm actually giving it an acceleration, but then after it's flying through the air, it starts with this high positive velocity. This is the 0 axis. This is the time axis. Sorry, the time axis. So it starts with a positive velocity, slows down, reaches the apex of its motion, and then starts speeding up in the negative direction. And we have this nice parabola for our position time graph, which says the same thing. Okay. Again, the uniformly accelerated motion always looks like this. The position versus time graph is a parabola. The velocity versus time graph is linear. Now, this is a special type of motion. This is free fall motion. This is a motion of an object traveling in just the y direction under just the influence of gravity. We're going to ignore the air resistance in this case. And what we're going to see, I want to find the slope of my velocity versus time graph, because the slope represents the acceleration. And again, if you had to do this on your own, if you had to do this from your own graph, you got to find the rise over the run, pick 2 points, find the rise over the run. Here I can just use the computer to calculate it, and I find a slope, which at this point I know is the acceleration. Specifically now, the acceleration due to gravity. And in this particular simulation, or in this particular experiment, I get a value of, I'm going to write it down here, of negative 9.57 meters per second squared. And that acceleration is actually, we give a special symbol for it. Instead of A for acceleration, we call it little g. Little g just means the acceleration due to gravity at Earth's surface. Now, this is our experimental value for little g. Our experimental value. The thing is that if I did this in a vacuum chamber where there was no air resistance, I would get a larger number for g, or larger magnitude of number for g. The accepted value for g is negative 9.81 meters per second squared. The reason there's a discrepancy here is, again, because we are neglecting air resistance and there is some error. This is a high school lab. The people that come up with this number here, they use much more sophisticated equipment than we do in a high school lab. But we are pretty close. This is within just a percent or two. So that is pretty close. We will be using this number all year. Very often, we approximate it as about 9.8 or even sometimes we just approximate it as about 10 meters per second squared. In the coordinate system that says up is positive, though, it always points down. That's the direction that gravity pulls things. So the acceleration due to gravity is typically a negative. We consider it to be negative. But again, you can define down as the positive direction in your coordinate system, and then the acceleration would just be positive. All right, that's about it.